Am I ready to go? I'm ready to go. Okay. Let me just move this out of the way. Okay, so I am your friendly NuSTAR expert who came here today to tell you about NuSTAR. So maybe before I do that, I want, because your student or some of your students, you may want to know how did we end up here. So maybe I'll just give you a brief introduction of myself and how I ended up here. So I'm originally from Denmark, and that's where I did my bachelor, my master's, and PhD. And actually, I was recruited in a horse stable. I did my master thesis in astronomy, and then I was looking for a PhD project. And there was a cowboy, a Danish cowboy. It's really weird, but he actually exists. Danish cowboy called Kristin, who knew a lot about X-ray mirrors. He is. He knows all about multilayers, and he was the driving force between behind NuSTAR, how NuSTAR came to be. So I met him in a stable because I also ride horses. And I said, well, I'm a physicist. And he's like, well, I have this project. Would you like to work on it? Okay. So I went there. I was an astrophysicist, and now I got into X-ray optics, and it turned out I'm really good at X-ray optics. So I kind of stuck with X-ray optics. And so first I worked as my PhD on this balloon mission called HEF, which is High Energy Focused Telescope. So that was a collaboration between Caltech and Denmark. And so I went over as my PhD. I was dumped in the desert, New Mexico desert, sat there with a balloon, flew it in a year, went back, wrote my thesis, and then I got hired by Caltech, who had been behind this balloon mission, to work on NuSTAR, which came after HEF. HEF was sort of like the precursor for NuSTAR. So we started HEF. We started NuSTAR, and that's how I ended up at Caltech, and I stayed there for 13 years until a couple of years ago. I was recruited by Goddard to come work on Athena, but I have still continued doing NuSTAR, and much of the calibration, at least when it's optics, that's me. NuSTAR is my little baby. So I'm going to tell you a little bit about that. And I here in the break, I was talking about the physics of the optics and the multilayers to a lot of people down there. So I'm happy I have quite a few slides in there about that. So I can give you a little bit more the physics behind multilayers and how NuSTAR is actually able to go to broadband beyond 10 kV, what you don't see in the soft X-ray instruments. So here is NuSTAR.
Is it true, the rumor that you rode from Los Angeles airport to Pasadena on the horse?
No. It's a good story, though, if it had been true. Okay, so here we are. Here's NuSTAR. So it's a very long observatory. It's got 10 meters, and that mast that you see there, the boom, when it was launched, it was squished together and it just expanded. There is a nice video, but for some reason the video doesn't work on my computer right now. So fortunately, I can't show you the cute video. So NuSTAR has two instruments and they are identical. And I wanted to name them something spiffy. We didn't get around to it. They're just called focal plane module A and B. Quite boring. And optics module A and B. Although you never see the name OMA, OMB. People usually just say FPMA, FPMB. I really wanted them to be Batman and Robin, but I wrote it down. So NuSTAR, just in context with Chandra and XMM, you see that we overlap in the 3 to 10 kV, but then NuSTAR kind of takes over from there and goes all the way up to 80 kV. Now, the other thing, there are other hard X-ray instruments up there, but they are all collimated. So we haven't talked a lot about collimated instruments. Matteo didn't mention it in his little overview, or did you?
No.
So there are collimated instruments, and one of them is integral. You may or may not know it. So really what that is you've got an enormous detector, usually cesium, CZT, the same stuff that we have, except you've got an enormous plane of it. And then you've got this enormous lead mask on top of it. And then you can just see the shadow pattern. You can tell where sources came from. But as you can kind of tell, you've got enormous background and you've got very poor angular resolution. So, maybe something like 3 arc minutes or 3 degrees where your source is not very accurate.
So this is where the focusing optics that NuSTAR has really revolutionized the energy band between 10 to 80 kV, because now you have actual focusing. You can focus your spot to a tiny detector. You can get rid of all that big background. You have an integral, and you actually have some energy, you actually have angular resolution. You can tell where the spot is, not to 3 degrees but to 3 arc seconds. So just to show you what that looked like, what was that big increase? The top, you see, that's the collimated instrument. That was from Integral. That was how well Integral could do the galactic center at hard X-rays. And then NuSTAR came along, and you can see you can actually see the point sources in much, much more detail. So NuSTAR was launched in 2012. So we are now 11 years in. It's a small explorer. So as you can see, it's actually, when it was, as you see it there, it's 300 kilograms. I think you said 4 tons for XMM. This is tiny compared to XMM. It was so tiny that you actually don't launch it on a rocket that goes straight up. You launch it underneath an airplane, and it's a little less, what do you call, spectacular. You sit there and they go, oh, they dropped it, and you don't really have, it was in the middle of the night, you don't see any, you just know that they dropped it, and then you just hope for everything. They no longer do this, by the way. They no longer do the Pegasus, so it was called the Pegasus rocket. They no longer do this because that plane is like 50 years old, and there's no other plane. It's it's very rare, L1 something. Anyway, they retired it, so now they no longer do this, and all small explorers are now launched on Falcons, like XP was. XP was supposed to fit in here, but they retired it. So the last, okay, I gotta tell you the story. So the Pegasus, as you see there's that little rocket. So the last mission to launch on this Pegasus, and this is very low budget, and you'll hear why this is low budget. The last thing to launch on Pegasus was a solar explorer. No, it's not a solar. It was ICON. It was an Ionos, looks at the ionosphere. And they had this rocket sitting on a trailer, and someone forgot to hook the trailer on the tractor, and it rolled off. The rocket rolled off. They didn't have anything in it, but it caused a 6 months to a year delay. And there's just a lot of problems, which is why they retired this method. So anyway, NuSTAR is in low Earth orbit, so we are not so high. High Earth orbit was, you have XMM, you have the ISS for NICER. We are what's low Earth orbit, and that's about 600 kilometers, and we are in equatorial orbit. So we are like 6 degrees away from the equator. This helps us because it's very low background. It's a very background benign area. It does mean that you run into what's called a South Atlantic anomaly. We do run into that. And so one orbit is 92 minutes. So when you see the NuSTAR data, you have Earth occultation, and you've got SAA that's going to chop up your data. So here is a light curve, as you see, and that light curve, you can see there is about 40 to 50% of the observing time, you are staring at the Earth. We're not reslewing, we just stare at the Earth and you go past. And then you also have these SAA passages that come in between, and they have a different beating than the Earth occultation, which is why you see these funny gaps in the data. Now this is an image of the background. You see this thing in the background here, and someone asked, and I'll get back to this. So this is the South Atlantic anomaly. It gets automatically cut out of the data. The instrument knows when it goes through it because it has an anti-coincidence shield. It knows the radiation got really high, turns it off. There is this thing called the tentacle, which sticks out from the South Atlantic anomaly. Sometimes it's strong, sometimes it's not. We don't automatically cut it out. So we do have some background tools for you to estimate whether or not we need to remove it, but I'll speak about that tomorrow. Okay, so effective area, you've heard a lot about it. Here is a NuSTAR effective area, which shows you why we get all the way up to 80 kV. So I'll do a brief talk again about how the optics work. So when you got an incident ray, you have part of it gets reflected, part of it gets refracted. And what we utilize for, at least for the soft X-ray instruments, is this idea of total external reflection. So you can kind of see that the refracted X-ray actually bends towards the surface, right? So if it bends towards the surface, the angle is smaller than the incidence angle. The refracted angle is smaller than the incidence angle. So as you decrease your angle, at some point, it becomes so small that that refracted ray actually comes out the top. That's when you're in the regime of total external reflection. And that's what the soft X-ray instruments takes advantage of. And this plot shows you, so it shows you, so there is an angle for the outermost shell, there's an angle for the innermost shell. The innermost shells has the steepest, or what you call the shallowest angles, and that's where your hard X-rays come from. The outer one has a less shallow angle, and that's where the soft X-rays come. So if you plot what is the angle of the inner and the outer on this plot where you have this angle of critical, so this is the angle at which that particular energy will be totally externally reflected. So you can plot that, you can plot this curve, and then you can put in the angles of your instrument. And so, for example, let's do XMM because that's what we deal with here, you can see that at 15 kV, nothing on XMM can totally reflect 15 kV photons. At that point, it's no longer efficient. You can also see that that all the shells, the entire instrument, totally externally reflects everything below 7.5 kV. So that's just a way to see how efficient the instruments are. You can study this at leisure. There's Athena, which we're going to talk about at the end of all of this. So how do NuSTAR actually get the hot X-rays? And this is, we mimic what happens in crystals. So we use constructive interference. And if you have a crystal, you have Bragg's law, which tells you that the specific distance between your crystal lattices gives you a specific energy where you have constructive interference. So that's how we don't have a crystal. What we have instead is we have multilayers. We have two different multilayers. We have a heavy multilayer, a dense multilayer like platinum, like tungsten. And then we have a light multilayer like silicon or carbon. And what you do is you make it look like it's a crystal lattice. And the important point here is that the interface between the low and the high and the dense, the low and the dense material is very sharp. That's what makes it look like a crystal. So you utilize that concept, and you also utilize the fact that you have multiple of these interfaces. So at each interface, you have a probability of reflection and refraction or transmission. So some of those photons, if you only had one layer, it would be lost. But since you have multiple layers, you have another chance to do another reflection, another chance to do another reflection, and so on and so forth. So that's what happens here. So this is what an X-ray, here's at a specific energy. How is it difficult to see? Then, oh, it's good. Okay. Yeah, so you have a specific energy here. So this is, I don't even know what the specific energy is. I didn't write it down. So it's for specific energy, it's probably 8 kV. So at 8 kV, you've got a multilayer that has 10 bilayers, so it has just 10 layers in it. And they are all at the same distance, which is this 65 angstroms. And so you have the first Bragg peak, so that's where n equals 1. Then you have the second Bragg peak, that's where n equals 2, and so on. And then you've got these little things there, which are kissing fringes, which are interference between the 10 different multilayers. So that's what it looks like. But you can see right away that this is not very efficient if you want a broad bandpass, having these peaks in there. So what you do instead is you vary the distance between the multilayers so that you shift that Bragg peak through the spectrum, all the way through it. So you have the thick layers at the top, which do the low energies. You have the thin layers at the bottom, which do the hard X-rays. And so you just kind of shift that through there. So here's an example again, the green curve, which may not stand out very well. So you have, if you just had one thick layer of platinum, which is in this case 30 nanometers, it would just have a drop off at a certain point, and it would never recover. Then you have a platinum carbon multilayer that has 10 bilayers. This is the red curve. And you can see there you've got the Bragg peaks coming up, but you've got nothing in between. And then you've got the green curve, which is a multilayer, which has depth graded thicknesses of the layers. And now you've got this broadband spectrum. So here's what the optics look like. They're glass. The glass that you have in these, they're slumped in an oven over a mandrel. The thickness of that glass is 0.2 millimeters, and it's the same type that you have in your phones. It's the same company that makes your glass in the phone is what is on NuSTAR. And then it gets glued down on graphite spacers, and that makes up the optic. So the PSF, it's not as good as XMM. And the reason for this is that they are pieces of glass. They're a little bit flimsy. They're very thin. And you glue them down. That means you're over constraining it. And that does cause it to get a PSF that is on the order of 1 arc minute. So that's what the typical PSF looks like. And you can see that like XMM, you've got these spikes. And the spikes are where you have over constrained the mirror. So that's why you get those. So moving on to the detectors. So we got cesium. Now you messed me up, Mateo. You have cadmium, zinc, telluride detectors. They are crystals. They're actually grown in big boules, and then they cut them out. So they're crystals, and you make the pixels on them by putting down lithographic anodes on it and putting a bias voltage across it. That's how you create an actual pixel. So there are 4 crystals on there, and each one of them is 32 by 32 pixels. Now we do a little trick with NuSTAR because we can actually have sub-pixel resolution. So we divide each of these pixels into 5. So the actual pixel pitch that you will see in your data is 2.5, about 2.5 arc seconds. So here's just a geometry. It's a small detector compared to what you've heard from XMM, MOS and PN. It's a small detector. The field of view is 13.5 arc minutes. So it's a 4 centimeter. And in principle, you've got 65, so you've got 128 by 128, and you've got 2 of those. So the hybrid design, just some details if you're really interested. So each pixel itself is 0.6 millimeters and divided into 5. They're actually glued down with epoxy. So the crystal itself gets glued down onto an ASIC. Not very fancy, but it works. And so you've heard this before. When you have a photon that interacts in the medium, you create electron hole pairs. And because you've got a bias across the cathode and anode, they migrate to either direction. And in NuSTAR's case, we read out a 3 by 3 pixel, which means we have 9 pixels. And there's a charge cloud, and the charge cloud actually registers in the other pixels around it. And by using that information, we can tell where the pixel actually went. We just calibrated it in our laboratory. We just took an X-ray source and scanned it across. And so we know if we see that sort of pattern, we know that it had a sub-pixel resolution where it actually happened inside the pixel. So we used information around it to actually figure out where it was. So the ZZT spectrum itself, it's not as good as CCD spectrum. And so at about 60 kV, you've got 0.6 kV. At 100 kV, you've got about 1 kV. So not great, but not bad either. So detector efficiency, the detectors are really efficient all the way up to 40 kV. Then you start seeing efficiency loss, and that comes from the different thicknesses of the detector. So there's an important thing you need to know about NuSTAR, and that's Deadtime. And you will encounter it probably in papers, and you may or may not encounter it yourself. But there's an important thing that happens in NuSTAR that's different from other detectors. When a photon hits the detector, it freezes the entire array. We are really counting pixels. We're not reading out an array. When we detect that there is a hit, the whole array freezes until we've read out that 1 photon. So while we read out that photon, so it takes 2.5 milliseconds to read out that photon. during that time, we will not detect any new photon. So that creates a little bit of a feature or a pattern. So if you look, for example, at millisecond pulsars, here you see the crab, there's a 33 millisecond pulse profile of the crab. You can see the top, which has the dead time distortion, that right before you hit the first peak, you have this enormous dip, because at that point, the highest probability of getting a photon is right at the first pulse profile, but you are now actually killing the detector. It's not detecting right after that, which is why you get the dip. So you can dead time correct it. That's a little bit, it's not hard to do, but it requires some specialized knowledge to do it. Most of the time you will not have to worry about it, but do be aware that it's something called dead time, which means if you've got a very bright source and you say you had it for 20 kiloseconds, but your dead time was 50%, that means you really only observed it for 10 kiloseconds.
Can I ask a question?
Mm-hmm.
So can you just explain what the dotted line is here?
Dotted line. Okay, so that picture in that, yeah. So the dotted line. So the solid line here in the top, that is the pulse profile without the dead time correction. This is just because the detector froze out for 2.5 milliseconds. So the dotted curve is the dead time. So you can see how the dead time goes from, this is normalized, but it increased by 30% right at that peak, and then it came back up. And then when you get to the second peak, the dead time increased again. So that's how that works.
So all this is taken care of. All that's taken care of by the pipeline. You don't have to worry about it. But if you want to show pulse profiles like for millisecond pulsars, like from the crab, you do have to know a little bit to do that. So NuSTAR operations, there are some web pages here. You can go click on them yourself at your own leisure. Like NuSTAR, like most all X-ray observatories, we have what's called announcement of opportunity. This is where you can do proposal. It's once a year. We just had ours, so the next one is in January 2024. So what's NuSTAR good at? Well, it's good at broadband spectroscopy. Obviously, it's 3 to 78 kV. It's good at hard X-rays, and it's also very good at bright targets, because we do not have the same pileup problem that CCDs suffer because of this way that we freeze the detector. Now, I say, if you have something that's super bright, and we're talking 10 crabs, like with NuSTAR, there is a pileup issue too with NuSTAR, but it's like 0.1% of sources get that high. So let me just spend the last time here just going through a couple of the source stuff that you can do with NuSTAR. So one of the things you see here, this is one of our first nature results that got out of NuSTAR. Before NuSTAR, you had the spectrum, and you had from NGC 1365. And there was an idea that there was just a hint with the XMM data that something was happening. And the model, there were two models that could fit the spectrum. Either you had gas obscuration around it, or you had gravitational distortion. You couldn't tell it because you didn't have the hard X-rays. When you got NuSTAR, it was very obvious it was one model over the other. The same then for like Compton thick AGN or AGN that are obscured. That's where NuSTAR stands out as well, because we can look through the dust where things happen. And in this case, for this NGC 1068, it's actually a combinatorial. Sometimes you see more of the source, more of the spectrum come through. Sometimes it's more obscure. And it's been looked at 4 times. You see here, there's many papers on it, kind of cataloging its behavior with the clumpiness of the torus. Now, the other thing that NuSTAR is very good at is looking at the extreme physics of accretion. And I'm not going to go into this because there's 2 talks that are going to tell you a lot more about it. We're very good at what's called X-ray binaries, the same as NuSTAR. So NuSTAR does a lot of work with their X-ray binaries, go through state changes, and they do it all the time. And so a lot of the science coming out of NuSTAR is suddenly an X-ray binary does something, and everyone goes and looks. And then you track it through the state change. You know, how does it accretion disk change? How does it how does its the corona changes and all these different things. You'll hear a lot about it later on, but that's what NuSTAR is very, very good at. Cyclotron lines. Cyclotron lines are typically from sources that have high magnetic fields and that accrete at the same time. They pop up in NuSTAR a lot because they're typically at harder X-rays. So you can do cyclotron lines. Pulsars, there's a lot of pulsars out there, and NuSTAR's timing is pretty good. So there's a lot of work that you can do in pulsars. Here's just a couple of examples. Glitches in pulsars, phase shifts in the pulse profile as a function of energy. You see that a lot as well. Here are a couple of examples. And cross calibration. So let me just briefly, we've already heard about IOCheck multiple times. And you've also heard Jeremy talking about this cross calibration on 3C273. So I did the first version of that when NuSTAR went up, and he's now doing the second iteration. But if you want to know because NuSTAR is very good with other observatories. So you want to know when you use it together with other observatories, the spectra are not going to match perfectly. They're going to be offsets. And so you can go to all this, the cross calibration site from IOCheck, where we have plenty of papers where you can see what happens if you have two different observatories and what kind of offsets you can expect. So if you just look up at these plots over here, let's do where do we have XMM? Oh, this is Swift XMM. Here. So here's NuSTAR XMM right here. So you've got the NuSTAR, the FPMA, FPMB, and you've got the MOSes 1 and 2. They all kind of say the same thing. And then you've got PN being off, saying a little bit different. And down here, we've got flux, and here we've got photon index. So that means if you do PN and NuSTAR, you probably will see an offset. You probably see that the flux in PN is lower than it is in NuSTAR. This is expected. It looks like that the photon index might also be a little softer in PN versus what it would be in NuSTAR. So you can go to these files and look at what has been done before. Now, there is a problem with bright sources, and we've not solved it. But when you do bright sources with NuSTAR together with, for example, Swift or XMM, we do see big differences, and we haven't resolved it. Some of it comes because you've got pileup issues in the other instruments, and maybe the model isn't quite right, but there's also another thing, which is dust scattering halos, which was mentioned by Carlos. So dust scattering halos tend to be around, well, they tend to show up if you've got a bright source. So if you've got an X-ray binary, you have this dust scattering halo, and I'll talk a little bit more about it tomorrow. But depending on how big of an extraction radius you have, you're actually changing the spectrum. So there is a degeneracy. You're not comparing apples to apples when you have bright sources between different instruments. So just be aware that if you have a very bright source, you tend to see these tails pop up at either end. This is sometimes background, the background subtraction from Swift in this case is maybe not as good. This is actually XMM. You've seen these tails there too. So don't panic when you see these things. This is known, and unfortunately, we don't have good answers to you how to deal with it. How does NuSTAR point? When I had actually made this slide a long time ago, and for some reason, I had seen one of those other ones, and it's not as bad as the thing dancing there, but it is. It's not great either. So we do. It's a long mass, and it's soft, and it kind of wiggles around a bit. So we have what's called a metrology system, and we've got star trackers that tells it how to reconstruct. So it's kind of a fun thing to do, and you should do it if you do NuSTAR data. You should go when you do DS9, and you can switch the different coordinate system in DS9. And if you switch it, for example, to what's called the Det1 system, which is what it looks like on a detector, you can see you've got an extended, the spot is kind of like spread out. Now, we have this metrology system that told us how does the mass move, how has it been dancing during this observation, and also we have a star camera that tells us where we're pointed. When we combine those things, voila, angels sing, and we've got a point source. So that's good. I'll talk a little bit more about this tomorrow. I'm showing it today because I'm going to return to it tomorrow, because NuSTAR can point at the sun. or very near the sun. Actually, we can point at the sun, but we can go, sometimes bright X-ray binaries love to go off when they're near the sun and no one can look at them, but NuSTAR can. The problem is when we do that, we blind the front facing camera. We can still look, but we can't do this neat reconstruction. There is a method for it, and that's what I'm going to discuss tomorrow. So I'm just highlighting this to you right now. There are other features with NuSTAR that are less fortunate, and that is ghost rays. So in a normal optic or in a X-ray optic, when you've got perfect reflection, when you got the right focal length and everything, you have two bounces. You hit the upper mirror, the lower mirror, you go to your detector. You can have ghost rays where you only hit the top one or you only hit the bottom one. XMM has a neat pre-collimator or stray light baffle that takes care of those. NuSTAR is cheap and does not. So you'll see these features. Here's a ray tracing of it. Here's what it looks like in reality. We've got actually different things showing up here right now. You may see this. So here's the ghost rays. You can see they're quite distinct because you've got these petal patterns. And then you've got this big thing up here, which we call aperture stray light. And that's another unfortunate feature of NuSTAR, which we've made lemons out of it. So you've got these aperture stops in NuSTAR, and there are angles where a bright source can actually slip right through and cause that pattern up there. We have used that to do an excellent calibration using the crab without going through our optics and get very precise measurement. But for many people, this is just very annoying. I'm sorry, we'll fix that in the next iteration of NuSTAR. So a little bit about background. Background in NuSTAR has a ramp. It's not even across the detector. So this just to be aware of it when you look at your NuSTAR data and you notice there is a difference in the background across the detector, it's perfectly normal. Don't freak out about it. And that's simply because the field of view from the detector is partially blocked by the optics bench, but not all of it. And so depending on how you look, you get that ramp across the detectors.
Yes. So are you going to tell about how to perform background subtraction correctly, how to choose a background?
We'll do that tomorrow.
Okay.
Yeah, we'll talk about that tomorrow.
Okay, so here's a background spectrum just to show you. It's composed of different things. It's composed of what we call the aperture flux, which is just background coming straight in. Then you've got internal background lines, and then you've got some solar background coming in. So that's typically what it's composed of. Now I'm gonna briefly, I have like 10 minutes, right? Something like that. I'm gonna talk about some other special things of NuSTAR and things that have changed since and some issues. Carlos mentioned micrometeorites. We haven't gotten hit on our detectors by micrometeorites, but there is some indication that we got our MLI. So our optics are covered in this, foil, tinfoil. It's called MLI, multi-layer insulation. And there's an indication that the backside of one of the optics, it has ripped open. Did it get hit by a micrometeorite? No one knows. But the temperatures are kind of going wonky donkey there. So we know that happened. And we also, for the longest time, people started telling us that FPMA was weird. And I didn't believe them for the longest time. No, that's not true, because you didn't always see it. They would send us these plots and I'd be like, that's weird. And then I'd go look at it at another epoch and it looked perfectly fine. Turn out that because you've taken away some of the MLI, which usually absorbs low energies, and it's apparently moving when we do momentum, it just kind of opens and closes. Sometimes you get more X-rays through. So if you take that into account on FPMA, you can correct that with just simply removing the multi-insulation from the response files. Now, as I tell, it actually has time dependence. We don't quite know how something can blow in space, but there is definite evidence that when the temperature sensor becomes cold, it has opened up to space, and sometimes it closes up again. So we have implemented some, corrections for it, but they don't always work. So if you see difference between FPMA and FPMB, don't panic. It's probably the MLI. And in that case, you listen to FPMB because FPMB is not broken. FPMA is. Okay, and then I'm finishing up with my instrument summary, which is just showing you that, and I'll just take some questions then. Okay.
We have 10-15 minutes for questions. Yes. Sorry.
Thanks. I'm really interested in the multi-layer optics and how they were developed. In the optical console, we had also multi-layer optics developed at Livermore.
Oh, okay.
For,
Yep.
Optimizing from the UV to the red using a combination of aluminium and silver as the metallic reflectors, but with other layers of dielectrics in between. And I know that that was a long, long time in the making. So I'm fascinated to know a little bit more about how they developed it. Was it a commercial group? Or
No.
a lab or what?
This was all done at DTU in Denmark, so the Danish Technical University. My advisor, Finn Christensen, he is the one that started it, and they're also the ones working on the Athena coatings right now. So he developed it, and the first time it was flown was on the balloon mission, and we had tungsten silicon. So multilayers are a little bit of alchemy. You need to find the right pair that go together. Some of them don't marry very, very well, and some of them just love each other. So tungsten silicon and platinum carbon are one of those. They really love each other. So we flew tungsten silicon on Heft, and that was developed for that. And then we did platinum carbon for NuSTAR to get that extra energy band. And that's what Hitomi has flown as well.
So were all those mirrors made in Denmark?
Yeah. So they were coated in Denmark, and we had a backup coating chamber in the US that helped us out, but they were literally all coated in the chamber at DTU, which now does all the coatings development for Athena. So all university stuff. Yeah.
I am excited by, the large energy range which NuSTAR is able to, provide us science about. But when XMM was being presented, and I found that XMM is not growing any older. Is that also something expected of NuSTAR?
That XMM is not what? Sorry, I missed it.
Growing older. It's like expectancy. Yes.
Oh. Oh, so what the NuSTAR lifetime is?
Yes.
Yes. So NuSTAR has no consumables. The only consumable we have is a laser on there that's slowly degrading. But we should be able to stay up there for another 10 years. The other danger is our orbit decays with the solar. If the solar is really active, it breaks and we go down, and at some point that long mass is going to catch in the atmosphere and becomes unstable. So that's really the end, is we get too low. We can't lift it up, but there are no consumable. So, getting hit by a micrometeorite, having technical issues on the observatory, that's the danger.
So you don't want to keep it like go to a higher orbit, or
We can't. So NuSTAR has no, so the question was, can we go to a higher orbit? No, so NuSTAR has no propulsion, unlike XMM. We maneuver with flywheels. So you've got big momentum wheels. That's how we turn around. So we just slowly sink in the atmosphere as drag pulls us down.
I have one question regarding ghost rays. So, for example, if ghost rays come to your source, like for example, ghost rays are that it comes to your source center. So, how do you suggest that we model for it?
Yeah.
Or how we should correct it?
So there are different things to do if you've got ghost rays. So if you've got ghost rays like this and your source, so it depends on where's your source. If your source sits on top of the ghost rays, we know we have pretty good track of ghost rays, and we know to put the source on top of the ghost rays. So, but it can happen. If your source is on the ghost ray, then your background is in the ghost ray. You have to take it from the same. If your source is outside the ghost rays, you know, let's say you're sitting here, you should just try and get it. Well, this is unfortunate, but this was very rare. Let's say this never happens, having both of these issues at the same time. If your source is here, you just take a background outside of the ghost, outside of these stray light or ghost rays. Yeah, the spectrum of ghost rays is a little hard to predict. You need a ray trace, and you need to be very careful about it. But you know, okay, let's say your source is sitting. If your source is sitting in one of these petals, you should try and take where you have that petal. You take it from the same petal if you can, because then you're trying to, because it sits on top of that petal. You can't move it. Yeah, so then you subtract it from the source. Sometimes you can do it, sometimes you can't, sometimes you have to. So sometimes this is we'll talk about this more tomorrow, but backgrounds are dominant in different energy bands. So one thing is to look at the background, the ghost ray background by itself, and look at your source, and then you may be able to tell that your source is so bright in the same energy band as the ghost ray, it doesn't matter. In that case, because with your source, where the background matters is where your source stops to approach that. So if your ghost ray is already gone by that time, you don't need to worry as much about it. So always look at the background spectrum itself versus.
Maybe one last one.
Please ask in the mic.
I see two focal plane instruments there, but they are of the same energy range.
Yeah.
What is the difference?
They're identical, they're two identical instruments. And that helps you a lot because if you see something in one and you don't see it in the other, it's usually instrumental. If you see it in both of them, you can be pretty sure it's real. You know, because you for source spectra, right? You want to squeeze every last photon out of some of these things. And usually you go after really faint things. Let's say this, like you go after really faint features in the spectrum. Some of them can be caused by instrument. If you only had one source, you would not be able to tell, but by having two very identical instruments and you see it very clearly in one, but not at all in the other, you can kind of, it's probably an instrument, it's not real. But if you see it in both of them, your probability that it's actually real just goes up.
In your fit with the focal plane module being with and without
Yeah.
MLI, what does 64% mean?
What does, okay, good.
Which seems to be a magic number.
Yes.
So
Well, so it changes. So let's go a little bit over this more in detail. I didn't want to exhaust you with the excruciating detail here. So let's see, or you wanted to see the fit. Well, let's look at this first. Okay, so there is, it varies. So here, so this is the correction that's in the CalDB. So we have a fixed number. For example, this is 90. So the percentage says how much MLI is left. So 64% means there's 64% of the MLI left. You're missing 34% of the MLI. There's a whole 34%. So here the correction in the CalDB is that this is 92, or this is 90, 95, 92, and then 90. These are flat, but you can see that there's a lot of variation, and there's these things, these cold fingers that we've seen twice. They come in clusters, which seems that somehow you made a SNU and it opened up really far, and it got really cold. We can see it in the temperature, and then suddenly this decreased, and that's where this particular fit actually comes from. This comes from one of the very cold ones. This is probably the largest MLI fraction missing I've ever seen.
we don't see them very often. So we have a web page that shows which ones have it, and which ones doesn't.
So these are not holes, so this is essentially
There's a
a,
rip, I think
it's
there's
a
a
rip,
here.
so that is basically what you're showing here is a covariant function
Mhm,
of the,
MLI, yeah.
of the MLI.
And we think, because it tends to go, you slew, and then you arrive, and now it's in the temperature has a different behavior. So we think as you slew and the momentum stops, that thing just moves out of the way. Depending on how you slewed, it opens up more or less. And on top of that, there's a temperature sensor around there, and we think it's come loose. We used to use the temperature sensor to track it. We can't do that anymore because it's gone crazy. It came loose. So there's 3 temperature sensors. There's 3 temperature sensors on the optic. Ooh, oh. Somehow there, 3 temperature sensors, and we can kind of estimate that the rip is somewhere between 5 and 3. So we use 4 as our to track. This is good. Now we think 5 has come loose because we used to take the difference between 4 and 5 seem to be stable. Come loose now, so we can't do this trick anymore, which means we may have to think of new ways for people to correct the MLI, because we can't do it with the temperature anymore. This is an evolving story. I think everyone's tired.